Okay, so in this video, we're going to talk a little bit about this idea of the moment of inertia and sort of try to understand conceptually what that is and where it comes from. So here I have a barbell that has two masses at the end of it, and we'll say that the distance from the center of mass to one of the objects is r, and it rotates in the plane this way. So not as you've kind of seen in some of the other pictures that we have on the notes where it rotates in the plane like this. It's actually rotating in and out of the plane around like that. And so in fact, each mass traces out a circle, say like this, and it does so with an angular frequency of omega. And we want to be able to sort of calculate the kinetic energy associated with these objects. So we can do this in the usual way, which is adding up the kinetic energy of each object. And so we will keep track of each one. They both have the same mass, but we want to pay attention to their speeds just in case they are different. And so we're going to add those up like that. Now the thing that we have to be careful about is thinking about what are those speeds when these objects are rotating around this axis in and out of the board like this. And so if we take a top view of what's going on, let's say look at the top object. It's rotating around in a circle like this at a constant angular speed, but the distance or the radius of that circle that it is actually rotating around is not r, this distance between the object and its center of mass. It's actually something a little bit smaller. It is precisely this distance, which we'll call r perpendicular because it is perpendicular to the rotation axis. Now we can determine this in terms of the angle theta and so forth, but we're not going to worry too much about that. What we're going to say is that this is r perpendicular, and so the speed of each of these objects is r perpendicular times omega. And so when we put that into our kinetic energy formula to calculate what the total kinetic energy of this system is, what we're going to find is that we end up with 1/2 m r perpendicular squared omega squared plus the same thing, 1/2 m r perpendicular squared omega squared, because this object here is also precisely r perpendicular away from the center of this circle. So I'm going to get rid of this here in the middle for a moment because we're going to work with this other equation for a bit. So we're going to clean this up a little bit. We know that all of these objects sort of, or these components of the kinetic energy share a common mr perpendicular squared. So we're going to group these terms together, and we're going to find that we end up with 1/2 times mr perpendicular squared plus mr perpendicular squared times omega squared. Now this kinetic energy is written in a way where there's something that keeps track of how fast the objects are moving. That's this omega squared. So this keeps track of how fast. And then there's this other piece here that keeps track of something very different. And so when we think about this, this thing is actually keeping track of how easy it is to rotate these objects around. So I'll convince you of that in a sec. We're going to rewrite this equation for the moment as 1/2 I omega squared, where I is this part in the brackets. Now let's make an analogy here. If we talk about the usual kinetic energy, which is 1/2 mv squared, the v keeps track of how fast. The m keeps track of how easy it is to change the kinetic energy of the objects. The larger the mass of the object, the harder it is to change its kinetic energy. This thing in brackets here, this m perpendicular squared, the sum business that we've called I, actually keeps track of how easy it is to change the rotation rate of such objects. If you have a large I, then it's harder to change the rotation rate of objects. This I is what we would refer to as the moment of inertia. So let me clean this up. So this idea of I, of adding up all the masses of individual objects times all their r perpendicular squareds, this is the moment of inertia. And really, it's a convenient conceptual tool for understanding how easy it is to get things rotating. Objects that have known sort of shapes, like spheres and rods and so forth, we have calculated the moment of inertia for these objects. And we know that it's, for example, easier to rotate a rod than it is to rotate a sphere because it has a smaller, say, moment of inertia, for example, than this particular sphere. So this concept is more of a tool for us to understand this rotation rate, but it also becomes quite easy for us to use when we're thinking about bulk objects because we have formula for them that don't involve these additions. For example, the sphere has a moment of inertia of 2/5 the mass of the sphere times the radius squared. That's rotating the sphere about its center, where rotating a rod about its center, a very thin rod, has a moment of inertia of 1/12 the mass of the rod times the length squared. So we can think about the kinetic energy of these really large sort of bulk objects when they are rotating because we have this concept of moment of inertia. If we didn't, we would have to add up all the kinetic energies due to all the little atoms inside to deal with that. But because we can describe it in terms of the moment of inertia, it is much simpler to do.